So today it's a big pleasure to introduce Dmitry Kerner from the Ben-Gurion University. And today he will talk about the equivalence of germs, of maps and set, of over K, where the K is a field, right? And versus this over an extension K also, right? And so it's your turn, Dmitry. Thank you very much again.
Thanks, Rodrigo. So it's a pleasure to see you all. Yes, my dream is to come to Brazil sometime. Don't know when, but at least I'll try to present something which I did. Now, my strong suspicion is that most of this is very well known, but I could not find it anywhere. All the questions are very naive and somehow not very complicated. The answers are more or less expectable. So if anybody at any point recognizes something which is known, I would really love to see the references. So feel free to interrupt me at any point. Yes, and please ask questions not at the very end, but after any sentence, because I don't have too much material. So let's start. Here is the abstract. I will speak about analytic maps. So let's start with real analytic maps. Yes, all the time I will speak about germs. We work very locally near the origin, and this is the totally classical situation. Yes, suppose we have two such mapping germs, and we consider them up to the coordinate changes. For simplicity, let's change the coordinates only in the source. Yes, this is the most classical situation. Here is the group of automorphisms of Rn. These are analytic automorphisms, local. And then the question, suppose two different map germs are related by a complex analytic automorphism. So the map germs themselves are real analytic, but suppose there is some intricate complex analytic automorphism that sends one map germ to the other map germ. Then can we actually cook up a real analytic automorphism? Yes. So if you start to work over reals, we don't want to get to other numbers. Yes, and that's
for example, sum of squares and the difference of squares. Yes, then exactly. They are equivalent as complex, but not equivalent as reals.
Yes, exactly. Yeah, so the answer is obviously no. However, as you can see on the third line,
so in the source and the target, you need to the even dimension, right? Because you have R to the 3, how to define the nodes?
The dimension is not necessarily even. It is Rn, any n. Just the moment you allow complex changes, you instead of all the real constants, you plug in complex constants. Yes, this is.
Just as mine in the first example, you just have from C2 to C. X1 plus X.
Wait. This is an abstract. On the next page, I will give this example, and
okay.
So this is just an abstract. Yes, let's go more or less quickly over the abstract. Yeah. So my first observation was that if we don't allow arbitrary coordinate changes, but insist that coordinate changes are unipotent in some sense, I will explain later in which sense, then having a unipotent complex equivalence forces a unipotent real equivalence. Yes, so the answer is actually yes, provided you consider only unipotent coordinate changes, and this can be reformulated. So we have the group of right equivalences. We can consider it over complex numbers, and if we take the orbit of the unipotent subgroup over complex numbers, in general it will contain lots of complex maps, but we intersect. Yes, we insist that we see only the real maps. We intersect with the set of real maps. Then we will get the real orbit, the orbit of the real unipotent group. And the first question is whether it is well known. Somehow I asked some people, nobody acknowledged that it is known, though people said, yes, it somehow should be something of this style. So this is the first very basic result, and then the immediate application. Suppose we have a family of maps, yes, we deform, unfolding, take a deformation. If it is right complex trivial, then it is right real trivial. And now we do not assume any unipotence, it's just arbitrary deformation and arbitrary complex trivialization. The next part of what I will speak about, so once again, we start from a real map, real analytic map. Yeah, this is the line number 5. And we invoke all the complex coordinate changes and then intersect still with real analytic maps. We know that it is not just one orbit. Yes, we'll get something which splits into several orbits. And the fact is that the number of orbits is finite, which is useful. Yes, one could expect some infinite collection of orbits if the singularity is rather complicated, maybe moduli, but it so happens that the number of orbits is just finite. Yes, to classify these orbits is a complicated question, but at least it is finite. Now, the geometric interpretation, yes, of real versus complex equivalence. Here, up to now, I spoke about maps. We can speak about germs of sets, yes, or we can speak about germs of foliations, and we pass from real to complex equivalence of this object. Yes, up to now, I spoke about real and complex analytic objects, and as usual, since everything is algebraic, you don't need real numbers, you don't need complex numbers, and all this holds much more in a more general setting. So the source can have arbitrary singularities. It is not necessarily smooth. The target can have arbitrary singularities. And there is nothing special about this particular group of right automorphisms, right coordinate changes. The whole, the results, they stay the same for all these classical groups: real, right, left, right, contact. Yes, and the extension of field, it is not necessarily real to complex numbers, and actually we don't even need fields. Actually, we need rings, even in the real case. So what is really needed is that this extension from little k to capital K is a faithfully flat extension of the local ring.
But what about quaternions? For instance, if you consider quaternions, it will be also like this, right? Your theory will...
Sorry, I'm a commutative person. Quaternions are non-commutative. I'm sorry. So maybe part of the theory works, but I never worked with in non-commutative world.
And a periodic field will work, right?
Yes.
Could you explain what is a faithfully flat extension?
Yeah. We are still in the abstract. This is the first slide.
Thank you.
So and later I will speak about. So now just one remark. The last line of this slide: the actions, the contact group, left-right group, the actions on the space of maps, they are very well known, very well established. I did not see any paper which addresses the case of singular target. Yes, there are papers that study what happens when the source is singular, but what happens when the target is singular, somehow I did not see. So if anybody knows, I will be glad to see some references. There are some technicalities because of the singular target. Some things do not get so smoothly. Okay, so now let's begin the talk. So take some analytic map, yes, real analytic map germ, and we consider it up to coordinate changes in the source, yes, as it was in the abstract. Yes, and so once again, phi x, it is a local analytic coordinate change. Usually I abbreviate it to automorphisms of the germ of Rn. And the question is, so suppose two such real analytic maps are equivalent under complex equivalence. Yes, does this imply the real equivalence? And the answer is obviously not. And here is the immediate example is left suggested. All the Morse points, they are complex equivalent, because by complex numbers we can eliminate all the signs. But they are not real equivalent because the signature is preserved under real analytic coordinate changes. So the answer is absolutely not. However, yes, so the modified question is then how to ensure that if you have a complex equivalence, then actually you will have a real equivalence. So what are the additional conditions? And the motivation, why would we think about this question at all? So suppose you are purely a real person, yes, but still in the proofs, sometimes it is necessary or at least simpler to work over complex numbers. Because complex numbers, they are algebraically closed, everything is solvable. So this is the very basic motivation. Now, more generally, so let's speak about maps. Once again, real analytic. Not necessarily real analytic. The whole theory goes easily. You can consider formal power series or analytic power series or Nash. Yes, some people don't like analyticity. They prefer something like semi-algebraic or very close to algebraic. And we have the classical equivalences. We have the right equivalence, yes, as I already mentioned before. Yes, again, formal or analytic or Nash, depending on your category, your situation. We have the left-right equivalence, the classical one. We change here the coordinates both in the source and in the target. Yes, and so we compose the target coordinate change acts on the left, the source coordinate change acts on the right, therefore it is left-right. Yes, and these phi y and phi x, they are automorphisms of the germs of our spaces. Yes, and the automorphisms are formal or analytic or Nash, depending on your case. And we have the contact equivalence. Now, the definition of contact equivalence, it demands drawing some diagrams. So currently, I will not even define it. Just it is something classical. Instead of it, I will speak about linearized contact equivalence, K-linear. So this is much simpler. It acts as follows. So a map is multiplied by a matrix. This U of X, it is a matrix non-constant. It depends on the variable. And also we change the coordinate. So this is a very particular, this K-lin, these are very particular transformations. Yes, and this, so the matrix UX, yes, its entries belong to this local ring, again, formal or analytic or Nash, algebraic. And the subgroup K-linear, it is a subgroup of the large group of contact transformations. It is much smaller. It is much smaller. However, there is some miracle, the very classical miracle that for any map, the orbit under the contact group coincides with the orbit under this much smaller linearized group. So it is, for me, it is a miracle. It is just miraculously works for contact equivalence. Such things do not work for, say, left-right equivalence. And this helps enormously. This removes many technical difficulties. Because of such coincidence, in some papers or books, when people speak about contact equivalence, they directly go to linearized contact equivalence. Okay, so, well, the question, let G be one of these classical groups, right transformation, left transformations, left-right contact, and how to ensure that if two germs of mappings are related by complex transformation equivalence, then they are related also by real equivalence. This is the first question. Another question, so as we know that in general complex equivalence does not imply real equivalence, so let's take the orbit under the complex group. Yes, it splits into many real orbits. Yes, the number of orbits will be certainly
Dmitry,
bigger. Yes.
Sorry to interrupt you, but can you split because you say the collinear group is smaller, but you say that at the end, if you are contact or collinear contact, what means the sense? Then you say smaller, so must equal? I do not understand.
We have two groups. We have the group of contact equivalences, K, and a subgroup of linear contact equivalences. I did not define what means K here. Just a fact is that K linear, it is a subgroup, and it is much, much smaller, infinitely smaller, if you wish. The group K is huge, and sometimes it is hard to work with. Yes, and what people usually do, they replace the genuine contact equivalence by linearized contact equivalence because the orbits are the same. So this is this was the idea.
Okay, thank you.
Yes, yes, and okay. So let's take the complex orbit of a map. It will contain many complex maps which we don't want to see. So we intersect this complex orbit with real maps. So we consider only those real maps which are complex equivalent to F. And this orbit will split into many real orbits. Can we get finiteness? Yes, at least. Once it is finite, you could ask about some maybe bounds on how many, but this is the next question. So first of all, we would like to see finiteness. Okay, and one more question. So suppose you work already with complex maps, and for some strange reason, you need to extend the complex numbers to some larger field, for whichever reasons. Yes, maybe the proof is so hard that you do various tricks, and there you should add some parameters, whatever. Yes, and then you will get a much larger orbit. Yes, with this capital K, and again intersect it with the only complex analytic maps. Will we get the initial complex analytic orbit? Yes, this is the question. So these are the three motivating questions which I would like to address. Questions? Feel free to ask. We are already on slide 2, and there are altogether just 8 slides. So feel free to ask. If well, hopefully
So
everything is clear.
The last equality is a question. Yes.
Yeah, it's a question. Yes, question marks. Yes, absolutely not clear why should it be true. You see, when we pass from real numbers to complex numbers, in general, we get much bigger orbit. And maybe the same happens when we pass from complex numbers to something even larger. Yes, the question is whether it is true or not. Okay. So once again, I just restate these questions. These are the questions from the previous slide. And well, here is the result. First, I state it in a very particular case. So again, we compare real analytic maps to complex analytic maps. So the first statement is that if two maps are complex equivalent, yes, and not just complex equivalent, but complex equivalent by unipotent transformation, I will explain later what it means, then they are also real equivalent and also by a unipotent transformation. So this is more or less the best we could hope for. Yes, the question is only what is this unipotent, how restrictive it is. So this is the first statement. The second statement is for the extension of the complex numbers. So here everything is very nice. If two maps are equivalent under some extended field K, then they are equivalent already over over C. Yes, the best we could hope for. So from now on, in your hard proof, you can, if needed, go to some very large fields, do there whatever you want, and then here's the little trick. Eventually, you will get equivalence over that same complex numbers.
One question.
Yes.
So this extension is as fields, not as a ring in this faithfully flat.
Currently, this is a very particular case of the theorem. So currently, for simplicity, I speak about fields only. Later, I will speak about rings. Yes.
Okay, thank you.
Good. The third part is that if we extend from real to complex numbers, then this complex orbit intersected with the real maps, it splits into a finite number of real orbits. Finite, the number can be very large, but at least it is finite. And finally, if you have a family of maps, deformation or unfolding, and suppose somehow you manage to show that it is complex trivial, then this family is actually a real trivial. And here in the last part, you don't need to assume any unipotence, just any family of maps. So this is the result. Now, again, my guess is that somehow this was very well known, at least maybe in 70s, and now it is forgotten. But I could not find the references. So, remarks. Now, what it means to be unipotent. A local coordinate change is unipotent if it can be presented as in the following way. So its linear part, it is 1 plus some nilpotent element, a nilpotent operator, yes, linear nilpotent operator, and terms of higher order, arbitrary terms. This is the definition of unipotence in this context. And you can see that in that example of Morse points, where you have plus goes to minus, it is that operator was not unipotent. Okay, and yes, and the same definition goes for left-right equivalence for contact equivalence. So roughly speaking, unipotence means that the linear part is identity plus something nilpotent, and higher order terms are arbitrary.
I have another question.
Yes.
Is the subgroup of unipotent automorphisms the sharpest group that satisfies this?
This I don't know.
Okay, yeah.
Not clear. But in some sense, my feeling is that it is, say, asymptotically sharp. That maybe in some cases you can do some tricks and extend, but not by too much, let's say.
I see. Thank you.
Okay, and regarding the third statement, the number of such real orbits inside this real part of the complex orbit can be large. Yes, I don't know any exact bounds, but probably this was even somehow studied. Again, I don't know references. Okay, so this is the first result in a very particular case. Let's I state it here once again. Now let's see the geometric implications. Until now I spoke about maps. Now let's speak about their zero sets or zero loci. So suppose for say for complex contact equivalence, we have again such a map and take its zero locus, but take it with multiplicities. For some reason, yes, I will keep multiplicities. And the fact is that if two maps are contact equivalent, then their zero loci are equivalent by coordinate changes, and with the multiplicities as well. And then the question is once again real to complex. Suppose we have two real germs inside the germ of Rn, and somehow unexpectedly they are complex equivalent. Does this imply that they are also really a real equivalent? Yes, and the same example of Morse point tells us obviously not. For example, you could start with just sum of squares. It will define just the origin. Yes, it is complex equivalent to this paraboloid or hyperboloid, probably hyperboloid. It is of real dimension n-1. Yes, and the two objects, though they look very differently, they are complex equivalent. And yet, despite this example, if the complex equivalence goes by a unipotent element, yes, in the same sense as I mentioned before, then actually there is a real unipotent equivalence. This follows from that theorem. Yes, so this is the geometric side of the contact equivalence.
I have.
Yes.
Sorry, I have another question. So, in your proof, you don't show. This is my question. You don't show that the unipotent equivalency that works in the complex. You don't prove that this is actually real, no?
No.
Okay,
you could have genuinely complex equivalence, yes, and yet there exists some other real equivalence. Yes.
Okay, thank you.
Now the geometric side of the left-right equivalence. So let's take a germ of foliation. Yes, we will take many zero loci. C is now a constant. As the constant varies near the origin, yes, we will see the level sets. Yes, for example, here is the classical one, when the function of two variables, x, y equal to c, and we will get many hyperbolas. This is the germ of foliation of R2 at the origin. And the fact is that if two maps are left-right equivalent, then the corresponding germs of foliation, they are also equivalent. Yes, there exists an automorphism of the germ of Rn that sends one foliation to the other. Yes, if you speak about formal maps, then the automorphism will be formal, and so on, analytic, Nash, and so on. And then once again, the same question, suppose there is a complex automorphism that sends one foliation to the other. Does this imply the existence of a real automorphism? And again, obviously not. And the same example works. And yet, if we speak about unipotent automorphisms, then complex unipotent automorphism ensure the existence of real unipotent automorphism. Yes. So I don't know. Such corollaries, they seem to be useful. Maybe they're actually used. Maybe they are very well known. Just they were not known to me. Yes, and last, the global version. Until now, I worked with germs only. But actually, we can get a little corollary in the global case. So take a family of real projective subsets in the projective space Pn, yes, the real, the family, T is the parameter. Now, if this family is globally projectively complex trivial, then it is actually real trivial. This is also a corollary of the theorem. So somewhat unexpectedly from the purely local consideration, one can extract some global corollary. Okay, so if there are any questions, I will be glad to answer. So basically, this theorem, this is, let's say, the main result just in a very particular case. And from now on, I will just generalize that same theorem to more general source and target and to arbitrary fields and so on. I will always speak about that same theorem, the same statement. So the results up to now were for these maps, real maps or complex maps. Actually, we did not use the smoothness of the source or the target. Yes. So we could start from a singular source and a singular target. So let's consider maps from X to Y. Yes. And here something should be explained. I don't know any reference, don't know whether it is very well known. So let's speak about left-right equivalence. We start from a subgerm inside Rn. Yes, it is defined by some ideal. Yes, maybe we work in formal category or analytic or Nash, whichever you prefer. Yes, this is subgerm defined by some ideal. And there are coordinate changes in Rn that preserve X. This is the group of out X. And it acts on X. The precise definition of this out X, it is the group of R linear automorphisms of the local ring, but I don't go into details now. And take a map from X to some target, whichever, and then we will get the action of this group of automorphisms in the source on the right. This is the right group, the traditional right group, which appeared already many, many times. And now we have the target. The target will be a subgerm inside Rm, yes, with arbitrary singularities, absolutely no restrictions. And also on the subgerm of Rm in the target, there is a group of its symmetries, its coordinate changes out Y. And this group in the target, yes, these coordinate changes in the target, they induce the left equivalence. So F gets composed with phi Y on the left. And then we have the left-right equivalence. Yes, F goes to, we pre-compose F from the right and compose from the left. Yes, this is the classical group of left-right equivalence. Totally classical, just now we have singular source and target. And now let's speak about the contact equivalence. So these are automorphisms of the product, X times Y, the source times the target, that act fiber-wise, and they preserve the slice, yes, the zero level, X times 0. So this K, it is a subgroup of the group of automorphisms of the product. And here I'm supposed to draw some pictures, but I did not have time and I don't have space. So I did not draw anything. So here is the precise formula. The xy, the point goes to the coordinate change in the source. Phi of x depends on x only. And in the second entry, we have a function that depends both on x and on y. And what the only conditions is that the zero level remains at the zero level, at the height 0. And also, if we restrict everything to the vertical slice, where yes, the y-axis, then we get an automorphism. So this is the group of contact transformations when the source and the target have arbitrary singularities. And again, this is something absolutely simple, but I did not see it written anywhere. Somehow, traditionally, people speak about smooth source and smooth target. Sometimes people consider singular source, but the target always was considered smooth. And well, this contact group, it acts on the maps, analytic maps, Nash maps, formal maps from X to Y. It acts in the completely classical way. Yes, this is the formula. Now, once again, the action in the case of the target, it is very well known, but it seems not for the singular target. There are various issues with this K group in the case of singular targets. I have two preprints on it. One is already on the archive. Another will appear hopefully on Thursday. Yes, and for example, instead of the traditional reduction from the contact group to linearized contact group, we have the reduction from the contact group to this K-lin F. It is not a group, it is a groupoid. In the singular case, this linearized version, it is not a group. You cannot multiply elements there. It is only a groupoid. Still, we can do our traditional things which we do in singularity theory. Good. So this is the version of the previous theorem. It is still a particular case. We consider maps as real analytic. You consider real maps versus complex maps. It will be one of the classical groups, and the same statements. If we have a complex unipotent equivalence, then necessarily we will have a real unipotent equivalence. And for the further extension from complex numbers to whichever field, if there are two complex maps and they are K equivalent, then they are equivalent already as complex maps. And this intersection, it splits into a finite number of orbits, as before. Yes, the singularities of source and target do not have any influence here. And finally, if a family of real maps is complex trivial, then it is actually a real trivial. Good. This was a little generalization from the previous slide, but it is still a particular case because we work over real and complex numbers. So here I keep this result. Now let's extend it to arbitrary field little k and extend it to capital K. So we will speak about maps over some field small k and large k. Yes, and the first question is, of course, why? Why would you like to do it? Well, for example, nobody likes real coefficients in power series. Everybody agrees that we want to see only integer coefficients. In the worst case, rational coefficients. But nobody wants to work with polynomials whose coefficients are just real numbers. And one more reason is that even if you work only with real or complex numbers, to prove the part 3 of the theorem, actually we must extend from a field to a ring. Yes, here we will, instead of just R, we will have the ring of convergent power series. So even if you work solely over real and complex numbers, you must at least work with rings over that numbers. So here is the general case. We will consider maps over small field versus maps over large field, actually not a field, rings. And as before, G will be one of the classical groups of equivalence. Actually, their definition does not depend on the base field or the base ring. The same definition works for arbitrary K. Of course, the properties will be different, but at least the definition is the same. Well, and there are some technical assumptions, which I will not state here. So the first part, yes, unipotence. Here you need zero characteristic. Suppose little k to large K to capital K is a faithfully flat extension of local rings. I will speak about it later. And take two maps over K, over little k. If they are unipotent capital K equivalent, then they are also unipotent little k equivalent. The second part holds for yes.
In this general case, what is X and Y?
X and Y, they are again germs inside Kn, Km with arbitrary singularities. Yes,
Okay.
and there are many technical assumptions. So roughly speaking, the germs are formal or analytic or K-algebraic in some
Okay,
sense.
thank you.
Yes. So I did not have place here to write all the assumptions, and if you, I will be glad to explain more. There are also preprints. Good. Now, second part is for K an algebraically closed field. Now of any characteristic, we don't need zero characteristic. And the statement is that two maps over little k, if they are equivalent over large capital K, then they are equivalent also over little k. Once you reach an algebraically closed field, then really you don't need to go any further. Or if for whichever reason you go further, extend it further, actually you stay, the final result will be over that same field. The third part is for a finite extension of fields. Yes, and not arbitrary finite extension, but there is extension of a very particular, it is called F-type. So we have splitting into finite number of orbits in the same way as we had from real to complex numbers. And finally, in zero characteristic again, if a family of maps over little k is trivial over capital K, then it is also trivial over little k. So this is the general case. This is the main result. And there are several things to explain what means faithfully flat extension and so on. So here I put this result for book tracking. Yes, and well, some remarks. So on remarks on part one, I will not give a definition of what it means faithfully flat extension, just some examples. So any extension of fields is faithfully flat, but if you start, say, from integers and extend to rational numbers, or if you start from polynomials and extend to algebraic power series, then these are not faithfully flat, unfortunately. So this assumption of faithful flatness, it is restrictive. Yes, ideally we would like to work with integer coefficients only, not even rational. Part one does not hold in characteristic P. You see, we assume here characteristic 0, and in characteristic P it does not hold. So, for example, here are two very simple polynomials. Now, suppose that this coefficient C, it is not a power of an element of the field, so we cannot extract the root. The field is not algebraically closed. Then the two polynomials, they will be unipotently equivalent over the algebraic closure, but not over the initial field. So this shows that the assumption of characteristic 0 is needed. And part one does not hold, say, for integers. Even in that case, yes, if we extend from integers to rational numbers, part one will fail. So here is an example. Take just linear function. Yes, compare it to f tilde with addition of some monomial, and suppose the coefficient c, it is at least 2. So it is not invertible in integers. Yes, so 1 over c is not an integer. Then the two polynomials, two function germs, they are unipotently equivalent over rational numbers, but not over integers. PT. Yes. So and so here you see that this, once again, faithfully flatness is needed. A technical condition, but it is needed, unfortunately. Now remarks on part 3. Yes, this what means F-type. The field must be of F-type. If it is perfect, and the Galois group of its algebraic closure is of F-type, and once again, the definition, the exact precise definition, goes via Galois cohomology, which I will not state here. I will just give some examples. So the real numbers, finite fields, periodic fields, they are of F-type. But the field of rational numbers, it is not. And there exist examples of polynomials with rational coefficients, and we take finite extensions such that this orbit over a finite extension splits into infinite number of rational orbits, which is something of pathology, but well, this is how the life goes. Yes. Okay, so, and somehow you didn't ask enough questions, so I finished too early. Thanks.